Okay, so we're starting 10.2 here. We're talking about series, and basically series we're going to see that are essentially they're the sequences we're doing, but where we're going to sum up the members of it. And so what we're going to want to do is calculate something like A1 plus A2 plus A3 plus so on and so forth to A to the N, and maybe more after that. And so we're going to do some things like nth partial sum, where we're going to sum it up through n, and we'll call that Sn. And basically that's just going to be this part right here all the way through a to the n, a sub n, a1 plus a2 plus a3 plus dot 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 a to the n, and we'd stop there. And we're also going to look at the limit as n goes to infinity for that summation as well. And give an example of that would be something like, 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus dot 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 dot. And so if we're looking at that, we can do some partial sums. So for S1 is just 1. And so we'll get a value and a suggested maybe expression. It's going to help us here. So we're going to want to take a look at these things like that. And so we look here, S1 equals 1, value is 1, and maybe we could do 2 minus 1. S2 is going to be, so I'll move that up a little bit, S2 is going to be 1 plus 1/2, and that gives us a value of 3/2, and that could be maybe 2 minus 1/2. And S3 could be 1 plus 1/2 plus 1/4, and that's 7/4, which is going to be 2 minus 1/4. And basically we can keep going like that, and we'll get the sum of the nth one, 1 plus 1/2 plus 1/4 plus dot dot dot, 1/2 to the n. Alright, so whatever one we're on, so 2 to the 0, 2 to the 0, 2 to the first, 2 to the second, so on and so forth. Plus symbol there. And we end up with 2 to the n minus 1 over 2 to the n minus 1. And so we can make maybe this minus 1 over 2 to the n minus 1. So basically looking at the pattern that's occurring and figuring out an expression that goes along with it. Okay, and there you go. You can see it right there. And that's what it's going to look like. So notice here that it says that it approaches 2. It doesn't say it equals 2. So not equal. We're not saying it equals 2. We're saying it approaches 2. So be careful with that. So let's take a look here. Definitions. Given a sequence of numbers a(n), an expression of the form a1 plus a2 plus a3 plus dot 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 is an infinite series. The number a(n) is the nth term of the series. The sequence, the set of Sn, defined by S1, S2, S3, all these sums here, is the sequence of partial sums of the series of numbers, Sn, being the nth partial sum. If the sequence of partial sums converges to a limit L, we say that the series converges and that its sum is L. In this case, we also write a1 plus a2 plus a equals this, and it equals that, equals L. If the sequence of partial sums of the series does not converge, we say that the series diverges. So this is kind of similar to what we had before, except we're summing them up, and either they're going to kind of add up to be a number or they're not. They're going to just, keep going crazy and blowing up to infinity or going down to negative infinity. And so you can see something like here, The sum of a series with positive terms can be interpreted as the total area of an infinite collection of rectangles. The series converges when the total area of the rectangles is finite. That's in picture A. And diverges when the total area is unbounded. Okay? Note that the total area can be infinite even if the area of the rectangles is decreasing. So just because they're decreasing doesn't necessarily mean it's going to converge. All right, so be very careful about that. And also take note that the sum with the positive terms can be interpreted as the total area. All right, the total area of them. So you're summing them, so you've got to add up A1 plus A2 plus A3 plus A4. You have to adding up all the areas of those rectangles. So let's take a look at a specific kind of series called a geometric series. These series are of the form n equals 1 to infinity of some number a times r to the n minus 1. And what that'll look like is an a plus a times r plus a r squared plus a r to the third plus dot 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 a r to the n minus 1 and plus so on and so forth. And this is going to just it's going to just basically be that summation. Okay, our ratio r that's basically going to be the number that we're going to want to pick, and then also our little number out front. So let's take a look at an example. And if we say r equals 1/2 and a equals 1, all right, then we can say that we get 1, that's a, plus a times r, so 1 times 1/2, plus 1 times 1/2 squared, plus 1 times 1/2 cubed, plus dot dot dot, plus 1/2 to the n minus 1, plus dot dot dot. And then that's going to go to being 1 plus 1/2 plus 1/4 plus 1/8 plus dot 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 1/2 to the n minus 1. And keep going like that. All right, so there's 1. We can also take a look at another example. And this time let's make r equal to negative 1/2 and a equal to 1 again. And this time what's going to happen with the series, you notice, because r is negative 1/2, whenever we have the odd exponents, like on this one and this one, we're going to end up with a negative result. And whenever we have an even exponent, like here, and one of the other ones, we're going to have a positive result. So we can basically write down the same one, but just alternate signs. 1 minus 1/2 plus 1/4 minus 1/8 plus all the way over to negative 1/2 to the n minus 1, and continuing on. All right, so now let's take a look at convergence. And I'll draw a little thing there. So basically here, if r equals 1, then our summation, Sn, is equal to a plus a times 1 plus a times 1 squared plus dot 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 a times 1 to the n minus 1, and that's just going to be a plus a plus a plus dot 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 plus a, and that's going to be whatever n is times a. So that's kind of a nice little situation. If r is 1, it's it's never going to affect it. It's just the summation of all your a's. And if we let n go to infinity there, then NA goes to infinity, and we end up with a divergence here. Okay, just going to keep blowing up there. If, second situation here, so let's do situation, if R equals -1, then this thing's going to bounce around, and we're going to end up getting a limit does not exist. If you think about it, it's we're going to get a minus a plus a minus a plus a minus a, and just going to kind of bounce back and forth between those. All right. If R does not equal plus or minus 1, then Sn is going to be a plus ar plus ar squared plus dot 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 a r to the n minus 1, and if we multiply everything by r, we get ar plus ar squared plus ar cubed plus dot 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 ar to the n now, because we're multiplying another r onto that one. And if we take and do Sn minus r times Sn, right, what you're going to end up getting is, you'll notice everything's going to cancel out. We're going to have an AR and an AR squared, AR cubed is going to cancel. And we even had an AR to the n minus 1. It was right before that AR to the n term. So it's all going to cancel except the AR to the n term and the A term. So what we're left with then is a plus AR to the n. And we can make this Sn 1 minus r, factor that out, equals a times 1 plus r to the n. And if we divide both sides, I'm getting a little bit out of room here, Sn equals a times 1 plus r to the n over 1 minus r. And at that point, we can let n go to infinity. Okay? And that gives us here, we've got, if the magnitude of r is less than 1, then the geometric series a plus ar converges to a over 1 minus r. So in other words, the sum of n equals 1 out to infinity of ar to the n minus 1 is going to equal a over 1 minus r. If r is greater than 1, so this is if the magnitude of r is less than 1. So in other words, r is a fraction that's less than 1. It's between -1 and 1. R between, I don't need to write that, it's right there. R less than 1, magnitude of r less than 1. If the magnitude of r is greater than or equal to 1, then the series diverges. So this is a very important result for you to know, so make sure that you have that down. And so let's go ahead and try using this a couple times in some examples. So here, show the following series converges. So we look at this. This is A, and this is R. So A equals 1/9, and R equals 1/3. Now, that means that what we can do here is have this become 1/9 over 1 minus 1/3. Right? We're just taking a look back at this one right here, a over 1 minus r, because r is less than 1. And so that's here, right here, the a over 1 minus r. Okay? And so we end up with 1/9 divided by 2/3, which is 1/9 times 3/2, which is 1/6. And there we go. That series converges to 1/6. Okay, so let's take a look at this next one. It says, show that the following series converges. So here, we can rewrite this as our sum from n equals 0 to infinity, and we're going to do -1/4, because if you notice, -1 is to the n and the 4 is to the n, so we can bring them together to the n times 5 and bring that 5 out in front. So here, again, we pick that number out in front. That a is a 5, and that r is a -1/4. So we know it's going to converge because the magnitude of -1/4 is less than 1. And then we can figure out what it converges to by doing that a over 1 minus r, which I'm going to leave, just for time's sake, I'm going to leave for you to do that little bit of math, but you should get 4. Okay, 5 over 1 plus 1/4. All right, let's take a look at our next little example here. And this is to express the repeating decimal 5.232323232323 as the ratio of two integers. So let's start with 5.232323, so on and so forth. We're going to say that equals 5 plus 23rd 1/100ths plus 23 over 100 squared. All right, so our 10,000 plus 23 over 100 cubed, because we're just moving back 2 decimals. Here's 23 hundredths, 23 10,000ths, and so on and so forth, just like that. Okay? Which means we can factor out this and make it a 5 plus a 23 over 100 times what we have here then is, if we're factoring that out of the first one, we have 1 plus 1 over 100 plus 1 over 100 squared plus so on and so forth, 100 cubed and on. And then this means we have 5 plus 23 over 100 times, and we can replace this with a sum from n equals 1 to infinity of 1 over 100 to the n minus 1. So when n is 1, this becomes 1 over 100 to the 0, and then it's 1 over 100 to the 1, and 1 over 100 squared, 1 over 100 to a third, so on and so forth. That is a geometric for us, where a is going to be 1, and r is 1 over 100. So that is 5 plus 23 over 100 times, again, a was 1, over 1 minus r, and r was 1/100th. And so this becomes 5 plus 23 over 100 times, this is going to be 1 over 99 over 100, so it's going to be just 100 over 99. We're dividing by 99 over 100, so I'm multiplying by the reciprocal, which is just going to equal 5 plus, and here we've got the hundreds canceling out, and we end up with 23 over 99. Okay? And if we really wanted this, we need this as the ratio of two integers, so that means this is, make them both have the same, so multiply this by 99 over 99, right? And you'll end up getting 518 over 99. Okay, so there we go. And let's go ahead and look at our last example for this video, and it's finding the sum of the telescoping series. You can't see me doing the air quotes with my fingers, but for some reason I did it anyway. And we've got this summation here. If you notice, this is not a geometric sum. All right. But, big but notice we can rewrite this. 1 over n times n plus 1. If we think of the partial fractions we've been doing, we can write this as 1 over n minus 1 over n plus 1, like that. And that means our sum, n equals 1 to infinity, can be as 1 over n minus 1 over n plus 1. Okay? And we can do a partial sum here. Sn is going to be, first off, when n is 1, 1 over 1 minus 1 half. And then, oops, forgot my plus symbol, plus 1 half minus 1 third, plus 1 third minus 1 fourth. And you might be noticing some pattern here, plus dot, dot, dot. If you notice this, we've got minus 1 half, plus 1 half, minus 1 third, plus 1 third. We'd have a minus 1 fourth and a plus 1 fourth coming up. And so we can kind of keep canceling through until we get to plus 1 over n minus 1. Oops, again. Minus 1 over n plus 1 over n minus 1 over n plus 1. So these are our last two terms. And this 1 over n minus 1 would cross out with the 1 over n minus 1 in the previous term. And this 1 over n cancel that 1 over n. And this is what we're left with. We're left with the 1 over 1, which is a 1, minus the 1 over n plus 1. So then we're going to let Sn, it's just going to essentially go to 1 as we let n go to infinity. Therefore, our sum from n equals 1 to infinity of 1 over n times n plus 1 is equal to 1. All right? Kind of a result that you don't necessarily expect to see coming there. But all right, anyway, if you need to, go back, look at any of these examples again, and I'll finish up this section hopefully in the next video. All right, thanks.